In this section, we'll talk about Selberg's asymptotic formula, which plays a key role in the elementary proof of prime number theorem. In Harday's book, the theorem is labeled as theorem 430, but I believe that is a typo. It should be labeled as theorem 433. There are two formulas in this theorem. The first one states that psi of x times log of x plus the summation for n less than or equal to x of lambda of n times psi of x divided by n is 2x times log of x plus big O of x. And the second formula states that the summation for n less than or equal to x of lambda of n times log of n plus the summation for all positive integers mn whose product is less than or equal to x of lambda of m times lambda of n is equal to the same right hand side, 2x times log of x plus big O of x. In the literature, you might have seen Selberg's asymptotic formula stated in other forms. But in this video series, we're going to state this as these two formulas, because they will be directly used in our proof of prime number theorem. First, let us prove that these two formulas are actually equivalent. The first observation is that this part is actually equal to this part. Why are they equal? Let's verify this. If you start with this sum and you use the definition for psi of x over n, and you plug in the definition of psi of x over n in terms of lambda, and you merge these two iterate sums, you get precisely the summation over here. And this verifies the second part of the left-hand side of the first formula is the same as its counterpart in the second formula. Now, to finish the proof that these two are equivalent, it suffices to show that the difference between the first term on the left-hand side of the first formula and the first term in the left-hand side of the second formula differ by something that is a big O of x. Once we show this, we are done. So we claim that this sum is equal to this psi of x times log of x plus a big O of x. How do we prove this? Indeed, we're going to use the Abel transformation 22.5.2. And recall, this transformation says, and we're going to use this formula with c sub n equal to lambda of n, f of t equal to log of t. And since lambda of 1 is equal to 0, we can take n1 to be 2. And it follows from this will summation 22.5.2, this formula follows immediately. Under this claim, you can immediately see that these two formulas are actually equivalent. So it suffices for us to just show one of them. In the following, we are going to prove the second one, namely 22.14.3. The formula appearing in this claim is quite important. We will see this again. And from now, we're going to give this a name, call it 22.14.4. Now let's prove this. The proof will be divided into two parts upon introducing an auxiliary summation. We define S of x as a double sum for each n less than or equal to x, and for each d divisor of n of mu of d times log of x divided by d squared. And we will show that the left-hand side of the Selberg's asymptotic formula, 22.14.3 plus a big O of x is equal to S of x, which is in turn equal to the right-hand side, and thus finish the proof. And now, let us first give the proof for this part. To prove this, we're going to start with the definition for S of x. What we do is that we're going to study first the inner summation for each n less than or equal to x. If n is equal to 1, then the summation is equal to simply log of x squared. And if n is bigger than 1, then the sum will be equal to, now let's break up this log of x divided by d squared. Because when n is bigger than 1, the summation of mu of d for d ranges over all divisors of n is equal to 0. So the first of the three terms is equal to 0. Specifically, this is by the theorem 263 in our previous section. And now we write the second term as negative 2 log x times for d divided by n of mu of d times log of d. And the last term is mu of d times log of d squared. Does this term look familiar to you? This guy also appears in our previous section of the video series. Actually, this is theorem 298. By theorem 298, this guy is actually equal to negative lambda of n, and there's also a negative sign in the front. So in total, the second term becomes positive twice log of x times lambda of n. So that is the second term. And we will keep the third term as it is. Therefore, s of x can be simplified as log of x squared plus the summation for n less than or equal to s but bigger or equal to 2 of this guy. And now we take this sum and simplify this a little bit more. And you might have seen immediately that this sum is precisely to psi of x. Notice that lambda 1 is equal to 0. To finish the proof of this part, we need to establish a very important identity. We'll show the summation of lambda of h times lambda of k for hk equal to n is equal to log of n times lambda of n plus the summation of mu of d log of d squared for d divides n. We prove this identity. The proof is by playing with the sum together with formulas in elementary number theory we introduced in the previous section. First, we're going to rewrite this sum as the summation of lambda of h times lambda of n divided h for all divisors h of n. And now we're going to use theorem 298 to this part. We'll change this guy to a summation of mu and log. Now don't forget this negative sign in the front. So here we used theorem 298, which we introduced in the previous video section. And next, we're going to flip these two sums. The outer sum will be over all divisors t of n. And the inner sum will be over all h, which are divisors of n divided by d. You can think of this as a Fubini type theorem. And now we see a divisor sum of lambda of h. And this reminds us of another theorem in the previous section, which says this sum is actually a log. And this is by theorem 296 from the previous section. And now let's continue. We'll break this log and thus break this sum into two parts. And you can notice that in the first part, we're going to use theorem 298. So by 298 again, this part is log of n times lambda of n. And we will leave the second part alone. Which verifies this claim. In Hardt's book, this equation has a name 22.14.7. So now we can use this claim into the sum by replacing this part with the difference of this guy and this guy. So by the claim, we rewrite this part as, and now we merge these two iterated sums. And at this point, we are very close to the end of the proof that the s of x is the left-hand side of this plus some big O of x. To finish the proof, it suffices for us to recall another thing we just proved. Recall the formula 22.14.4, which states that the sum here differs from the product here by a big O of x. And if we multiply both sides by 2, we get this equation. And because twice of big O of x still big O of x, we can remove 2 here. And now, if we plug this guy into here and cancel out this twice of log of x cosine of x, we'll get what? And because this log of x squared is also big O of x, so we can merge this guy into here, and we do a cancellation from here. Eventually, we're going to get, and this part is precisely the left-hand side of the Selberg's asymptotic formula 22.14.3. So we are done with the first part of the proof of the Selberg's asymptotic formula.